So if you have one plane of symmetry, so if you consider a plane of symmetry, we have a coordinate system and if we assume that the x1, x2 plane is a plane of symmetry, then we can, I'm going to use the same sort of notation we use for rotation matrix, but it's not a proper rotation. It would end up in a left-handed coordinate system, but it's a reflection, in fact. So if we examine the reflection, 0, 0, 1, 0, 0, 0, minus 1. And so this is a reflection about the x1, x2 plane, right? It takes the positive x3 and reflects it to the negative direction. So if we assume that, but we can treat this like a rotation matrix in the way it, at least in the sense of the way it would transform a tensor. So if we were wanting to look at how the stress, say a stress prime, the stress sigma transformed into sigma prime through this rotation, then we'd use this same equation, and what we'd get is sigma 1, 1. Something like this. And of course, whenever I don't write the bottom half of the matrix, it's because it's symmetric. I just don't want to repeat all those terms. So just to be clear, this is a negative here. And similarly for the strain. So strain would transform into a prime coordinate system like this, and you'd get that E31 is equal to minus E31, and E23 prime is equal to minus epsilon 23, and the rest are the same. So if we use these rotated values and we put them back into our generalized Hooke's law, and I'm just going to write out, all the terms for sigma 1, 1 prime. So sigma 1, 1 prime, all the terms would be so that's just replacing in, basically just writing out this equation for sigma 1, 1, just putting primes on everything, right? But now if we substitute these relations in here, so that some of the terms are in the unprimed coordinate system. so that the terms are in the unprimed coordinate system. So here I have a minus. So then, so this is my sigma prime stress, and I just made all, on the right-hand side, I just made all the substitutions back into the unprimed coordinate system according to that reflection. And if this is actually a plane of symmetry, then this equation should be equal to the equation in the unprimed coordinate system. I know this is kind of painfully explicit here. So these two guys should be equal to each other. So if they're equal to each other, if I subtract the two, if I subtract one from the other one, I should get 0, right? If they're equal to one another. Okay. So let's do that. If we subtract one from the other, then what I get is this equation. It's not 0. And the only way it can be made, the only way it can be 0 is if sigma 1, 1, 2, 3 and sigma 1, 1, 3, 1 is equal to 0. So that's the only way that those two equations can be equal to one another. And so if that's the case, then we can go on and we can make similar arguments. So I only wrote out there the sigma 1, 1 case. But if we wrote out the 2, 2, 2, the 3, 3, and we just kept making just went through and we made all these arguments, what we'd see is that 2, 2, 2, 2, 2, 2, 3, 1, 3, 3, 2, 3, 3, 3, 3, 1, those are all equal to 0 as well. Okay? And so then, for a material with one plane of symmetry, we have C1, 1, 1, 1, C1, 1, 1, 2, C1, 1, 3, 3. So then your material constants reduced to this. This is called a monoclinic material. It has 13 independent constants.